Okay, we want to look at some additional examples using projectile motion. So here is an example. We have a projectile that is launched from the edge of a cliff, and its initial velocity is given to be 12 meters per second at an angle of 60 degrees. So here we have our cliff, and we have our XY coordinate system. The origin is where we are launching from. So we have our V naught at 60 degrees, that's our angle theta there, and this parabolic path is going to be the path of the projectile, and we know that the initial velocity is 12 meters per second. Now the question says how far above or below its original level, so its original level is at the x-axis, so how far above or below will it strike the opposite wall that is 50 meters away. So we know the distance that the projectile is traveling is 50 meters. Okay, so let's look at how to analyze this problem. Okay, so what we're looking for here is the y value, the distance above or below the origin where the thing is going to strike. And so if we look at the y equation, we can figure out what the y component of the initial velocity is. That's just going to be found using our trig. But we don't know what the time is. We know what little g is, but again, we don't know what the time is. So we cannot use the y equation because we don't know what the time is. Or I should say, we can't use it yet. So as a general rule, in any of these projectile motion problems, if you know what you're looking for, distance, velocity, whatever it is, but you need the time, then you're just going to have to find one of the other equations that will give you the time. So let's look at the x equation up above. I do know the x distance that it travels, which is 50 meters. I can use my trig to find the x component of the initial velocity, so I can find v naught x pretty easily. And so the only thing I don't know in the x equation is the time. So I can solve this one for time and then plug it into there. So here we have the x equation. X is v naught x times t. We know that the x distance is given to be 50 meters. We can plug in the 12 meters per second that we were given the initial velocity is. And of course we know the angle is 60 degrees, and to get the x component we need the cosine of the angle. And so we can plug all of those numbers in and solve for t, and we get 8.33 seconds. Now, you can understand everything that I'm doing, but that doesn't mean that you can do it yourself. You need to be able to sit down and work these problems without watching the video. That's very, very important. You should always be doing that. Once I go through these problems in the video, you should write out the problem and then sit down with a blank piece of paper and work it out. And if you can't work it, then go back and look at the video. That process will make it so that you know this stuff solidly. If you guys don't put in the work to learn this stuff, you're going to do terribly in this class. You have to put in the work. So, I can't do that part for you. I can help you as much as you need, but you're going to have to do some work. So please, make sure you go through these videos. Make sure you understand them, but then work through these on your own without looking at the videos. When you can work through all of these examples without having to look back at the videos, then you have a really good foundation which you can then apply to your homework. If you're trying the homework before you look at these videos, you are just setting yourself up for failure, because this is a process, and so you have to get the basics down, then you have to learn how to apply the basics and expand your knowledge. So please, don't just follow these videos and just go, I know that makes sense, that makes sense. You have to be able to do it yourself without looking at the notes, without looking at the videos, with just what's in your head, because you understand how to work the problems. If you can do that, that'll get you ready for the test. But anyway, so what do we have here? We have found the time. The time is 8.33 seconds. And what is that time? That's the time it takes for the projectile to travel the 50 meters, because we plugged in 50 meters and we solved for the time. And of course, that's where the wall is opposite. So now we can find the height on the wall by plugging that time into the y equation. So the y equation we have is v naught yt minus 1/2 gt squared. And we just found out that the time was 8.33 seconds, so we can plug in our v naught, the sine of theta. So of course, this all together, that's v naught y. And of course, that's t. So I'm just plugging these in. This is 1/2 g. So I'm just plugging all these numbers in. That's of course the time squared. And so I plug in all those values into my formulas, and I end up with the height being negative 254 meters. So that means that the projectile will strike the wall, the opposite wall, 254 meters below its initial height. Now here's a fun example because it doesn't really have any numbers. And I know you guys hate the examples that don't have numbers, but it really does give you a strong way of thinking about these things. It's important that you guys not just think about these as formulas that plug numbers in. These formulas show relationships, and if you look at how these formulas behave, you can understand how nature behaves, not just work-specific problems. And so that's why we make you do this. It's a kind of a generalized knowledge that is much more applicable than the ability to work individual specific problems that you memorize. So what is a problem? It says a projectile is launched with some positive angle and initial velocity along a flat horizontal surface, and then it returns to that surface sometime later. So in other words, I've got a flat horizontal surface, I've got some projectile, it shoots up, it comes back down, it returns to that flat surface sometime later. And this projectile is launched with some initial velocity and some angle theta, and we want to find the angle theta that gives us the maximum range. In other words, if I shot it at a bigger angle, the projectile might do something like this, but it wouldn't go as far. If I shot it at a smaller angle, it might do something like that. It wouldn't go as far. So I want to find the angle so that the projectile goes the maximum horizontal distance. That's the problem. And so in order to do that, we need to come up with a general expression for the distance that a projectile travels along a flat surface as it goes. So for something shot at a positive angle, we know our x and our y kinematics equations. And so the x kinematics equation is just v naught xt, that's the x value, the horizontal range. And the y kinematics equation is v naught yt minus 1/2 gt squared. Now, of course, this v naught sine of theta, that's v naught y. Why did I write it like that? Because in the problem, I'm looking for theta. So anytime the problem is looking for v naught or looking for theta, instead of writing v naught x, you want to write v naught cosine of theta, because that'll give you a problem that has v naught, that's what you're looking for, or gives you theta, and then that's the case that we're looking for theta. So that's why instead of writing this as v naught xt, I've written that as v naught cosine of theta times t, but just know that's v naught x, and of course that's v naught y there. So v naught yt and v naught xt. But I've also added in, we know that y is going to be 0, because we're told in the problem it's launched and then it returns to its initial height. And so if I put my coordinate system like that, we know that y naught is going to be 0 and yf is going to be 0. And that's all the same thing. So I can plug in 0 for my y, and I'm looking for x. So what I'm going to do is what we always do here. I'm going to solve this equation for t, and then I'm going to plug it in up above. And so if I look at this equation, and I've made a mess of it with all my writing on it, but v naught sine of theta t minus 1/2 gt squared is equal to 0, there is a t in each of these terms, so I can factor one of those t's out. And so if I factor out a t, I get t times the stuff in the parentheses, v naught sine of theta minus 1/2 gt. And so that means that I've got t times this stuff in the parentheses. Either t is equal to 0 or the stuff in the parentheses is equal to 0. If either of those things is true, then this equation is solved. So I know that the projectile is launched at t equals to 0, so that gives me the route when it was at a height equal to 0 over here. So the stuff in the brackets must be the solution that corresponds to when it strikes the ground on the other side. And so if I set this equal to 0 and solve for the time, that'll give me the time that I'm looking for. And so when I do that algebra, I get my first solution, t equal to 0, and then my second solution, t equals to 2 v naught sine of theta divided by g. Now keep in mind our x expression was x equal to v naught cosine of theta times t. And so what I'm going to do is I'm going to take this t and I'm going to plug it in right there. And so I'll get 2 v naught, another v naught will make v naught squared, sine of theta, cosine of theta, all divided by g. And so that's what I end up, and this is an expression for the x position as a function of the angle. Now this is a little bit weird. I've got cosine of theta and I've got sine of theta here. It turns out there's a way to simplify that using a trig identity. In fact, if you recognize the identity, you'll know that this 2 out front is actually even part of that identity. So the identity I'm talking about is that 2 times the cosine of theta times the sine of theta is equal to the sine of 2 theta. So if I plug that into my formula for x, I end up with x equals to v naught squared times the sine of 2 theta divided by g. So now what I want to do is I want to find the value of theta that makes x the maximum value. And so how do you do that? Well, if you know calculus, you know that if you want to find the maximum or the minimum of a function, you can take its derivative and set it equal to 0. So that's sort of the go-to bag of tricks for people who know calculus. They just take the derivative of this and set it equal to 0 and then solve for theta. It turns out, though, we don't actually have to do that because the function sine of theta is so well known, we can just use what we know about it. Now, it gets a little bit complicated because we don't have sine of theta, we have sine of 2 theta. So just for the purpose of thinking it out, let's let 2 theta equal to phi, and then this becomes the sine of phi here, which, just for the purpose of thinking it out, so we know that if I plot the sine of phi, it looks something like that, and that its maximum value is 1 and its minimum value is negative 1. And so this function sine of theta, or sine of 2 theta rather, sine of phi, it is maximum when the sine is 1. And that occurs when the argument, this phi, or in this case 2 theta, when that's equal to 90 degrees, because the sine of 90 degrees is 1. And so when that stuff that's in the argument of the sine is equal to 90 degrees, then this is equal to 1, and this whole function is maximized. So all we have to do is set 2 theta equal to 90 degrees, and that tells us the angle for which you get the maximum value. And so divide both sides by 2, and there's your answer. The maximum value of a projectile range will occur when it's launched at a 45-degree angle. Now, in the real world, because there is air resistance, this isn't exactly true, but even with air resistance in a lot of situations, it's pretty close to being accurate. So, this is our answer, 45 degrees. That's the angle that gives you the maximum amount of horizontal range.